तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Okay, so today what I would like to do is to go to the states of the radiation field of the electromagnetic field, which would correspond respectively to blackbody radiation on the one hand, which is like what is called a degenerate photon gas or thermal radiation, and the opposite extreme to it, namely coherent radiation, like in a single mode ideal laser, and we will see what the photon distribution properties are in the two cases. So let me start with blackbody radiation, and I recall to you something from elementary thermodynamics which all of you know, namely that the energy density of the radiation inside a blackbody cavity is proportional to the fourth power of the temperature. This is the Stefan-Boltzmann law. And what do we mean by a blackbody cavity? Well, some container of some volume V in which there is radiation of all possible wavelengths going back and forth in thermal equilibrium. Therefore it is essentially a photon gas, a gas of photons of all possible frequencies, all possible polarizations and all possible directions of the wave vector. These photons are imagined to go back and forth between the walls. They get absorbed by the atoms in the walls and then re-emitted by these atoms, and if the system comes to thermal equilibrium at some temperature T, some fixed temperature T, then we know that the Stefan-Boltzmann law says that the energy density, the energy per unit volume, the average energy per unit volume inside this cavity is proportional to some constant times T to the power 4. That is the Stefan-Boltzmann. Now what I should like to do is to ask a slightly different question, namely what is the probability that the number of photons inside this cavity at a particular instant of, at any instant of time, the number of photons is a certain number n, okay. But once I say a photon, I have to also specify the frequency of the photon, I have to specify its wave number and so on. So we will focus on photons of a particular frequency, some given frequency omega and some fixed polarization, okay, and then ask what is the probability that the number of such photons is n, okay. Now one can do this problem rigorously by the following method. The gas inside here is a gas of photons, and we know that photons have 0 rest mass. So these are particles, essentially particles which move such that the energy is proportional to the momentum. E is equal to c times p, where c is the speed of light in vacuum, okay. But there is more to it than that. These photons have a spin quantum number equal to 1, therefore they are bosons, and it turns out that when you have a collection of identical bosons, total wave function of this boson system must be symmetric under the exchange of any two bosons. That is part of the rules of quantum mechanics, namely the fact that integer spin particles obey Bose statistics and they are indistinguishable, and the total wave function or the state of the system is symmetric under the exchange of any two of these particles, okay. Now this is going to, pardon me? What do you mean by total wave function? Yeah, what do I mean by total wave function? Well, in a simplistic picture, if I would like to describe the state of the system by some ket vector psi say, then under the exchange, physical exchange of the labels of any two particles, this state vector should not change, should be invariant. In the simplest instance, when you have two material particles and they have coordinates r1 and r2, and the wave function in the position basis for these two particles is some psi of r1 comma r2, then psi of r1 r2 must be equal to psi of r2 r1. But then of course you must also exchange all the other labels, the spin labels as well, everything is exchanged, and then in the case of photons the states are supposed to be symmetric. In the case of half integer spin particles, half odd integer spin particles like electrons, the states are supposed to be antisymmetric. Okay. Now the consequence of this is something I haven't gone into because we didn't have time to do quantum statistics, is that the number of possible particles in a given state, in a given one particle state of a collection of such particles, the number of possible particles in a given state is 1 or 0 in the case of fermions, and it can be anything in the case of bosons. That is all that we need to remember at the moment. Okay. Now what I will do instead of going into quantum statistics, is to derive this result, in particular something about blackbody radiation, so to speak, by the back door, and I will do this by a heuristic method. And all I am going to do is the following: I am going to look at photon of frequency omega, some given frequency omega, and a particular state of polarization, say left circularly polarized or right circularly polarized, does not matter. So photons of frequency omega and a given state of polarization. And for these photons I am going to ask the following question: what is the probability that in thermal equilibrium at this temperature T, this cavity contains n such photons at any instant of time, okay, and that probability I denote as Pn. Okay. Of course it is going to contain photons of all frequencies and all wave numbers and all possible both states of polarization, but I am focusing, as I said, on just this single frequency. Okay. Now what is this going to be proportional to? Well, each photon of frequency omega has got an energy h cross omega, because for a photon the energy momentum relationship is linear, and the moment you give me its frequency omega, angular frequency omega, the energy is h cross omega. Okay. So n of these photons would have an energy n h cross omega, and now comes the crucial point: these photons do not interact with each other very strongly. A gas of photons, they may scatter off each other in some sense, but the scattering cross section is really very weak. They do not interact with each other. They do interact with the walls of the cavity, and that is how the system gets into equilibrium. I put in some radiation inside a blackbody cavity and I wait for sufficiently long time, then the walls absorb these photons, re-emit photons at different frequencies, various frequencies, till an equilibrium distribution is reached. And all of you are familiar with the Planck distribution, which essentially says that the intensity at some frequency omega, the intensity curve does this kind of thing. So this is I of omega as a function of omega, and this peak here is dependent on the temperature. As the temperature of the cavity increases, the peak frequency increases, the average energy also increases. Okay. And this is the famous Planck distribution law. We are not going to quite derive that, I will get it by the back door, as you will see, but now we are asking a different question. We are saying I fix the frequency and I ask what is the probability of a certain number of photons. Okay. Now I know that if you have n of these photons, the energy is essentially n h cross omega. The probability that a subsystem, these photons form a subsystem inside the blackbody cavity, the probability that a subsystem has any energy E when it is put in equilibrium with a thermal reservoir at temperature T is proportional to the Boltzmann factor, e to the minus the energy over kT. So this probability is definitely proportional to e to the power minus beta h cross omega, beta is 1 over kBT. Okay. That we know from the Maxwell-Boltzmann factor. No matter what statistics these photons obey, the actual probability is proportional to e to the minus beta h cross omega, and there are n of them, so there must be n. That is the energy, n h cross omega. Now of course this is just a proportionality, the actual probability must be a number between 0 and 1. Therefore you must normalize this probability, and the way you normalize the probability is to sum over all possible values of n. Okay. But let us be a little more accurate in this. We know that the radiation field inside this cavity can be regarded as a collection of oscillators corresponding to different frequencies, and what is the energy of an oscillator in which there are n quanta? It is h cross omega and n plus half. So really we must keep track of that half too. It will turn out it will not matter in this calculation, but that is the correct answer. And what is Pn actually equal to? It is equal to e to the minus beta h cross omega into n plus half divided by a summation over all possible states of the system, in this case all possible numbers, right. So this runs r equal to 0 to infinity e to the minus beta h cross omega into r plus a half. Okay. So that is my probability. And it is a function of n out here. This is a summation index, it is just summed over and goes away, and that is it. So let us work it out. It is a simple geometric series. As you can see, this half factor here and this half factor cancels out, because this comes out of the summation and cancels on top and below, so it does not really play any role at all. So Pn is equal to e to the minus beta h cross omega n, which is this factor, and then this geometric series e to the minus beta h cross omega is a number less than 1, because beta h cross omega is positive. So this number is less than 1 and it is a geometric series, this number is raised to the power r, and therefore this is equal to divided by 1 minus e to the minus beta h cross omega inverse. Right. This is some x, and x to the power r summed from 0 to infinity is 1 over 1 minus x, 1 minus x inverse, and that is it. So we actually have a closed expression which says this is equal to, let us write this properly, 1 minus e to the minus beta h cross omega e to the minus beta. Okay. So it tells us in thermal radiation, for photons of a particular frequency and state of polarization, this is the absolute probability, and it depends on the temperature. You can see what the behavior of this thing is going to be as a function of temperature. Now what is the average number of photons? It's, by the way, it is easy to see that this is normalized to 1, we must check that right away. N equal to 0 to infinity Pn, this is also summed from 0 to infinity, and this will cancel this exactly, so it is clear that this is equal to 1. It's clear. So it is a normalized probability. Then what is the average number of photons? Average number of photons of frequency omega and a given state of polarization, otherwise you have to multiply it by 2. This is equal to summation n equal to 0 to infinity n Pn by definition. Okay. The first moment of this distribution. And what is this going to turn out to be? Well, this is equal to 1 minus e to the minus beta h cross omega summation n equal to 0 to infinity n e to the minus n beta h cross omega n. I have to sum this now, but with an n inside. Okay. And what's that sum? What kind of sum is that? So if you put x equal to e to the minus beta h cross omega, you have to do summation n equal to 0 to infinity n x to the power n, where x is less than 1. Now what is this series? This is an arithmetico-geometric series. So this is equal to summation n equal to 1 to infinity n x to the n, because the n equal to 0 term does not contribute, and let us write this as equal to x summation n equal to 1 to infinity n x to the n minus 1, but this is d over dx of x to the power n. So I pull the d over dx outside, x to the power n, which is x d over dx x over 1 minus x, okay, which is equal to x times 1 minus x the whole squared. If I differentiate that, I get a 1 minus x out here, minus x times, there is a minus 1 if I differentiate this, so this is equal to x over 1 minus x the whole squared. I think I am okay, right? Pardon me? Is this okay? Well, if the answer is wrong, we will soon know. Okay, so this is equal to 1 minus e to the minus beta h cross omega, that is 1 minus x, and then x, which is e to the minus beta h cross omega over 1 minus e to the minus the whole squared. Okay. So that this factor goes with that, and if I multiply through by e to the beta h cross omega, we get our result that says the average value of n is equal to 1 over e to the beta h cross omega minus 1. I just multiply numerator and denominator by e to the minus beta, e to the plus beta h cross omega, and then this is it. This is a non-negative number, as it should be here, but please notice that this number could become very large, it could be very small, etc. So we have two regimes. One of them is if beta is 1 over kt. So if you have h cross omega much less than kBt, so the frequency you are looking at in energy units is much smaller than the thermal energy, average thermal energy kT. What would this correspond to? This is like e to the x, where x is much less than 1. Therefore you can write it as 1 plus x squared and so on. The 1 cancels out and the leading term is just x, 1 over x. So n average goes like kt over h cross omega. Okay. On the other hand, in the other limit, h cross omega much greater than k Boltzmann T, this exponential is very large compared to unity and you can drop it, right. So n goes like e to the minus h cross omega over kt. This is a small number, a very small number. So it is clear that very high frequency photons are very improbable. You do not have too many of them on the average. If the temperature is not high enough, it is going to cut off extremely fast, exponentially fast. This number can get exceedingly small. For example, if you ask what is the probability of, and it changes very rapidly with the frequency, if you ask what is the probability of having optical photons at a very low temperature black body cavity, this number can become extremely small, much smaller than unity. On the other hand, in the other extreme, near the peak for example you would have a very large number, average number. So remember this distribution has this funny shape, it goes up and comes down, drops down exponentially fast. Now there is a better way to write this distribution, and that is the following. So let us use n average as a parameter. So let me put, instead of putting this cumbersome n average, let us put n bar equal to 1 over e to the beta h cross omega minus 1. This implies that e to the beta h cross omega is equal to, if I take it to that side, it is 1 plus 1 over n bar. So it is n bar plus 1 over n bar. So e to the minus beta h cross omega is n bar over n bar plus 1. Okay. So that helps us to write down this Pn in a very convenient fashion. Pn therefore is equal to, it is just this factor raised to the power n, and then 1 minus this factor, 1 minus that factor just gives 1 over n bar plus 1. So it is 1 over n bar plus 1 n bar over. So that is my distribution. This is the photon number distribution for photons of a given frequency and polarization in a black body cavity. What kind of distribution is this? It is some number which is less than 1, this quantity is less than, it's a fraction, raised to the power n. It is a geometric distribution because just this fraction raised to a power n. It is a discrete distribution, it is a geometric distribution. Because the different terms in this sequence Pn are like the different terms in a geometric sequence. It is just called a geometric distribution. But remember that n bar is a function of the temperature and the frequency. So the relation is very clear, n bar is 1 over e to the beta h cross omega minus 1. So at any instant of time in thermal equilibrium, if you ask what is the average number of photons of a given frequency, this number could be smaller than 1, why not? It means 0 is dominating. Remember 0 is also an allowed value, right? So this distribution has a 1 over n bar plus 1, and then P1 is smaller than P0, which is smaller than P2, etc., etc. So as the Pn increases, the P decreases in this geometric fashion, and P0 is in fact the largest out here. So the average could well be between 0 and 1, it could be a fraction. Okay. We already saw earlier that the probabilities can become vanishingly small depending on the temperature regime. So at any given temperature, this is the way the distribution looks. And if you draw the histogram here, what would it look like? P0 would be here, P1, P2, P3, P4, etc. It would go down in this fashion like some power. So it is conceivable that the average is sitting between 0 and 1, can happen. What is the variance of this distribution? And that is the interesting question to ask. So what is the scatter about this average value? That shape of that distribution already suggests that it is a very broad distribution, that there could be a large dispersion about the mean value. And the mean value for many distributions is not enough to specify much about the distribution. You need to know the variance, you need to know the higher moments and so on. So what is the variance going to be? And that requires the mean square. So let us compute mean square value n squared. This is equal to n squared Pn, 0 to infinity. We have to sum this, and that is equal to summation 0 to infinity. Let me write this as n times n minus 1 Pn plus 0 to infinity nPn. And this guy is just n bar. So this is equal to, by the way 0 and 1 do not contribute here, so there is a summation from 2 to infinity n minus 1 Pn, but Pn is 1 over n bar plus 1, and then it is this quantity, this guy here, let me call it r for a minute, that to the power n. Okay. Now what is this equal to? We can write this as the second derivative of r, so put an r squared here and r to the n minus 2 here, and this guy is d2 over dr2 r to the n. Okay. So pull this out, differentiate, do this calculation, it is a trivial calculation, and then you discover this, you must remember this factor here, this becomes twice n bar squared plus n bar. I remember this result because it is a well known series here, and it is twice n bar squared plus n bar. Okay. Therefore the variance of n equal to n squared minus n average squared, this is equal to n bar squared plus n. Okay. So it is actually quite large, it is larger than the mean value, and the standard deviation is the square root of this guy. So you could ask what is the standard, and remember all these are functions of temperature, so, and the frequency. So given this you could ask what is delta n over n, and that is equal to n bar squared plus n bar square root of that divided by n bar squared. And this is equal to square root of 1 plus 1 over n bar. Okay. So that is the relative fluctuation, and if n bar is small you can see that this can become extremely large. Otherwise, even otherwise it tends to 1, that means the variance, the standard deviation is becoming comparable, it is always bigger than the mean, it is becoming comparable to the mean if the mean is large, but if the mean photon number is small, this variance can be actually quite large. So although the mean value can be very small, the scatter about the mean, the fluctuations are enormous. So number fluctuations are very significant in this case, and this is not surprising because photons are continually getting absorbed and emitted, and therefore the number is not a definite concept. The number of photons is going to be a random variable, unlike material particles where the number of photons is fixed. So this system has very large number fluctuations. So this is an alternative way of looking at blackbody radiation, namely in terms of the photon statistics. By the way, once you have this result, then it is easy to compute what the internal energy is. This is the number of photons of a given frequency and a state of polarization. Now I ask what is the energy, average energy? Well, here is a quick way to do this. The internal energy of this gas is going to be an integral over the volume of the gas, etc. So let us look at the number density itself, the energy density itself, the energy per unit volume. This is going to come by integrating over all possible frequencies from 0 to infinity d omega. This is the average number of photons of frequency omega. Therefore the average energy, contribution to the average energy from photons of this frequency is just h cross omega multiplying this. So it is h cross omega multiplying e to the beta h cross omega minus 1, and you must multiply it by the number of photons that you can have in a frequency window d omega. because you are integrating over this d omega. And what is that equal to? Well, let us go back to our old phase space argument. In phase space, if you regarded these as as ordinary particles, material particles, the energy is going to be related to the momentum by linear relation E is Cp, and remember that the phase space had a 4 pi p squared dp, because the angle, the direction of the momentum does not matter, the whole thing is spherically symmetric. So in phase space, the d3p, the volume integral in momentum, that volume element had a 4 pi p squared dp, and for photons E is h cross omega equal to Cp. So this says h cross omega by C is p, and you need a p squared dp. So p squared dp is 4 pi into h cross squared omega squared by C squared, dp is h cross by C d omega. Okay. So you have to put that in here, so that is multiplied by 4 pi h cross cubed over C cubed omega squared, that becomes an omega cubed here, d omega is already there, and then you have to multiply this by a factor 2, because that is the two states of polarization that every photon could have, any photon could have. And the actual internal energy is this multiplied by the volume, but divided by the cell size in phase space, which in 3 dimensions is h cubed. Okay. So you put all these factors in, this becomes an 8 pi over C cubed and so on, so it is 8 pi over C cubed dot 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 something or the other, and then the crucial part is this d omega cubed over e to the beta h cross omega minus 1 0 to infinity. That is the crucial part. There are some constants multiplying it. They will contribute to the Stefan-Boltzmann constant. Okay. Now this integral is well defined, because as omega goes to 0, the denominator vanishes like omega, because e to the x goes like x, but there is an x cubed here. So the integrand is completely convergent at the origin. At infinity this blows up, but this exponentially blows up, and therefore this integral cuts off very fast. And this integral can be done by contour integration, for example. Its value is some given number, it's some pi to the 4 over 90 or something, some given number, finite number. Our interest is in finding out what is the temperature dependence of this without doing the integral. Well, that is not hard to do, because you can put beta h cross omega equal to x, for example, then it says omega is x divided by beta h cross. So this d omega is going to give me a 1 over beta, and this becomes a dx, and then omega cube is going to give me 1 over beta cube, so it is beta 4 out here. This becomes x cubed e to the x minus 1. So all this is some numerical value, and the whole thing finally is proportional to t to the 4, because there is a beta to the 4. So that is how the Stefan-Boltzmann law emerges. Notice how different it is from the classical ideal gas of material particles, where the energy is proportional to T. U is 3/2 kT per particle, U over n is proportional to T, it is the first power of T, but here it is the 4th power of the temperature out here. Very different from what happens in the case of material particles. Two things contributed to it. One of them was the fact that the energy was linear in the momentum or the frequency. as opposed to the formula p squared over 2m, which is what you get for the kinetic energy of a material particle of finite rest mass. In this case the energy is proportional to the momentum directly. The second thing was this factor, this Bose factor, the 1 over beta h e to the beta h cross omega minus 1, which arose completely from quantum statistics. It is a non-classical factor, and together these two conspired to make the energy proportional to T to the 4. Okay. Therefore the specific heat would be proportional to T cubed, and this is responsible for the T cube behavior of the specific heat of the photon gas. You can also go on to calculate the pressure, you can calculate the equation of state and so on. It is not hard to show in this case that P is 1/3 U. The pressure of this gas is proportional to 1/3, is equal to 1/3 its energy density, and therefore it too is proportional to T to the power 4. Contrast this with PV equal to RT for the material particles. In this case it is also an ideal gas, non-interacting photon gas, but because it is quantum statistics and because the energy momentum relationship is different, you get completely different behavior. Okay. So now that we know how to do this problem, let us go and ask, let's turn back and ask what happens in the case of coherent states of radiation. So let us go back and ask, what if I took these oscillators and put them in a coherent state, and where is this realized? Well, it turns out ideal single mode laser light is coherent light in this sense. It is well described by what we looked at earlier in the context of the harmonic oscillator as oscillator coherent states. So I am going to make this assumption without proving it too carefully, that if you have a single mode ideal laser light, then you have coherent radiation, and this is modeled by oscillator coherent states. Okay. I will explain in a minute why this is called coherent. What is coherent about it? Recall the oscillator coherent states. We defined, I don't know the notation, I don't recall the notation we used, I think we used alpha. I said this denoted an oscillator coherent state which was e to the minus half mod alpha squared summation n equal to 0 to infinity alpha to the power n over square root of n factorial. This state here was a number operator state, so let's say a dagger a on n was equal to n. So now I am claiming that if in a laser cavity, an ideal laser cavity, the single frequency omega and a single state of polarization, the radiation in that cavity is not in a state of thermal equilibrium. It is very far from thermal equilibrium, completely out of equilibrium, it is in a coherent state. Okay. These are number states. In other words, this state now you must think of as a state corresponding to a fixed number of photons, a given number, little n of photons, and you superpose all these fellows and you end up with coherent radiation if you superpose, make this kind of superposition. What is the meaning of this number alpha, this quantity alpha? Well, we immediately see that this alpha, which is a complex number, it has both a real part and an imaginary part, or a modulus and a phase. The modulus of it is in fact the n bar that we talked about earlier, because what is the probability Pn in this case, what is the probability that this state of the radiation field has n photons at any instant of time, exactly n photons. What is that equal to? Well, once you have written it in this form, the answer is staring you in the face, because this is a superposition of number states. So let us put R here. and the coefficients in the superposition are the probability amplitudes that the number is some r. So Pn of course is n alpha. This is the probability amplitude, and the probability itself is of course this. So what is that equal to? Yeah, it is just the coefficient of that. All you have to do is the coefficient of this. So this is equal to, the coefficient is this, e to the minus mod alpha squared, you have to square it, take the modulus and square it, then you have to take this fellow, take its modulus and square it. So mod alpha to the power 2n over n factorial, because if you square this guy you get this. This is it. So all you have to do is to put the ket, the bra n here, use the fact that nr gives you a Kronecker delta, that will pick out just one coefficient and then you take its modulus squared, that is it. What does this distribution remind you of? It is a distribution, it is a Poisson distribution, and what is the average value? Yeah, this is a Poisson distribution. It is a very different distribution altogether. You have already seen that the average number of photons, the average value of this quantum number n in this coherent state is in fact mod alpha squared. So that is the average value of photons. But this is precisely Poisson distributed, whereas the other one is a geometric distribution, it was n bar over n bar plus 1 to the power n. This guy is to write this as e to the minus n bar to the power n over n factorial. That is a Poisson distribution. What is the variance of this distribution? N bar itself. For a Poisson, it has this interesting property that the variance is equal to the mean. So in this case, so this is blackbody radiation. Blackbody, it is also called thermal radiation. On the other hand, if you have coherent radiation, variance of n is n bar itself, and therefore delta n over n bar, this guy here, is equal to 1 over square. That is a typical behavior of a Poisson distribution, that the relative fluctuation goes like 1 over the square root of the average. Now this alpha is at your control, you can actually change the alpha depending on the kind of laser, the kind of source you have, you can make this anything here. But the point is that it is very different from the other state of radiation. This has got a definite state of polarization, it is single mode, that is incoherent, it is random superposition of all possible frequencies, all possible wave numbers and polarizations, just the opposite here. So that is the reason why it is called coherent, but this is a classical state of radiation, as classical as you can get, as opposed to that, as opposed to thermal radiation, because when you have blackbody radiation, it is a quantum statistical gas, you use the rules of quantum statistics, whereas in this case, although it looks like this started with the quantum oscillator and so on, this is as classical as you can get, because you see, recall what we had said earlier about connecting the electric field to the oscillator, recall that the electric field E, in that case I had just one direction Ex, this guy went like A minus A dagger, so it was some A e to the I omega t minus A dagger e to the minus I omega t. Okay. And then of course to construct the field itself you have to sum over all possible wave numbers and so on. Now you could ask what is the average value of this field in a coherent state, in a state of this kind, and what is the value of the mean square, etc. And then it turns out, this is a simple exercise to do, that if you compute the mean square value of this, which is like finding the mean intensity, that looks like a classical wave. It is as close to a classical wave as you can get. The phase is uniformly distributed, it is completely classical, and the phase is distributed in a Gaussian pattern, I will show that, and it is as classical as you can get. We already know that this is a minimum uncertainty state. I would like to recall to you some things we did in the context of the oscillator. Remember that I pointed out that the electric field was like the x of this oscillator and the magnetic field was like the p of this oscillator, and in this coherent state of the oscillator delta x and delta p turned out to be as small as they are in the ground state of the oscillator itself, which is a minimum uncertainty state. So just to recall to you, delta x delta p was proportional to h cross into n plus a half, and when n was 0 this is as small as you can get. Those are the ground states of the oscillator, that is the ground state of the oscillator. And for an alpha, I plot delta x here and delta p here, this is the curve delta x delta p equal to h cross over 2, the minimum uncertainty curve, and in suitable units delta p and delta x were both here for the ground state of the oscillator and also for any arbitrary alpha. Okay. So in that sense the coherent state is a classical state, quote unquote, minimum uncertainty. Besides, the mean square value of the electric field, the magnetic field, etc., they behave like classical waves, as close to classical waves as you can have. The phase of this system, of the phase of this radiation field, the phase of the state is something we have not been able to define, because recall when I talked about the phase operator last time, I had difficulties because the number operator did not have a proper inverse. We need to overcome that and ask what the phase is, and here is how one does it. So let me define a state of definite phase as follows. A state of definite phase, let me call it phi. This is the definition, as equal to summation n equal to 0 to infinity e to the I n phi. So this is a number, it is a phase angle between 0 and 2 pi, and I define it by using these coefficients, because if the phase were phi for this state, e to the I n phi would be the factor that appears here summed over n. This is not a normalizable state, as you can see, because the coefficients in front have modulus 1. And of course you find what is phi phi and you end up with infinity as the answer. So it is not a normalizable state, but we are not interested directly in this state itself. We are interested in asking, given a state of the radiation field, what is the distribution of the phase. So if you give me an arbitrary state of the radiation field, then I would compute this quantity here and take its modulus, and this is equal to the probability distribution of the phase of the state, and this can be made well defined. And if you do this now for the thermal state as well as for the state of radiation, the blackbody radiation, as well as for the coherent state, then in the case of blackbody radiation you discover that this P of phi is uniform, which is physically acceptable. There is all possible phases, it is completely random between 0 and 2 pi. On the other hand, if you did this for the coherent state, then the phase distribution is a Gaussian, and if alpha is mod alpha a to the I theta, it is an arbitrary complex number, then this guy here becomes proportional to e to the minus phi minus theta whole square. So it is a Gaussian peaked about the phase of this complex number alpha. So that is the significance of what this alpha is in a coherent state. Its modulus squared gives the mean number of photons in that state, and its phase gives you the peak of the phase distribution of the state of the radiation. So this is how one defines a distribution in the phase angle. If you go back to what I spoke about, what I talked about with regard to the phase last time, you discover, you note that we had difficulties because we couldn't define the inverse of the number operator. So this was the problem, and we ran into difficulty defining a unitary e to the I phi, this operator. There are many ways of overcoming it, and one of them is as follows. Define the following. I know that a dagger A has eigenvalues 0, 1, 2, 3, etc. This is the number operator and does not have a respectable inverse and so on. But if I consider this operator, let me use some notation for it, let us call it A, which is equal to 1 plus a dagger A to the minus half times A, and its a Hermitian conjugate, which is a dagger 1 plus a dagger A to the minus half. I consider these two operators. This operator has an inverse, you can define minus half, etc., because this spectrum, this is a dagger by the way, and its spectrum is 1 plus the spectrum of a dagger A. So it is 1, 2, 3, 4, etc., instead of 0, 1, 2, 3, and then the inverse exists. Now what is this commutator of this A with, so what is a dagger? What does this become? This is equal to 1 plus a dagger A to the minus half a dagger, which is equal to 1 plus a dagger A which is the unit operator. There is no problem. On the other hand, a dagger A has a problem, which is a dagger 1 plus a dagger A inverse and then at A. And this of course you can't write as a unit operator, it is not true. But you can go back and ask, what is it, how close to the unit operator is it? If it were unity, then I could take this to be a respectable exponential operator and it would satisfy the commutation relations needed for the operator e to the I phi. But it misses it by a little bit, because although a dagger is unity, the unit operator, a dagger A is not. But you could go back and ask, what does this actually look like? What is the representation of this operator in this number basis, and what does it look like? It is clear that this is equal to summation n by completeness. That is certainly true. So what is this guy equal to? So work it out. Find the matrix elements. So all you have to do is to find the matrix elements of this operator on both sides. When it acts on 0, the state, the ground state, this actually ends up with a 0 here, because this fellow annihilates the ground state. When it acts on 1, what would it do? When it acts on a general n, what would it do? So let us find A dagger 1 plus A dagger A inverse A on a general n not equal to 0, 1, 2, 3, etc. What does this give you? This gives you A n equal to A dagger 1 plus A dagger A inverse, and then there is a root n and then n minus 1. And you have A dagger A, this fellow acting on n minus 1. A dagger A acting on n minus 1 is just n minus 1. 1 plus that is 1 plus n minus 1, right. So that is n and there is an inverse there. So this whole thing becomes 1 over root n minus 1. Now A dagger acting on n minus 1 gives you a root n with the same with n. It is well defined, right? There is no 0 here. Expand it in a power series and take term by term, right. You have to be a little careful to make sure this series converges, so there are 2 expansions you need to resort to, but when you do that it ends up with just 1 over n. A dagger acting on n minus 1 is going to give you root n on n, and therefore this guy here is also a diagonal operator except when n equal to 0, otherwise it gives you 1. So this whole thing, this operator can actually be written as I minus just the projection corresponding to the ground state. So it is not quite unitary, but it comes very close to it. In particular, if the average number of photons, if the contribution from this is small to the photon number, then you can neglect it and it is essentially unitary. Okay. So these operators A and A dagger play the role of e to the I phi, and we can use those to define reasonable phase operators, exponential of the phase operator. Okay. Alright, so I do not want to get further into quantum optics, I just wanted to point out 2 salient features. One was that in the case of thermal radiation, blackbody radiation, which is an ideal photon gas at some fixed temperature T, the photon number distribution of photons of a given frequency is a geometric distribution. In the case of coherent radiation, which is very close to classical radiation, a classical state of the radiation field, far away from the thermal, very far away in character than the thermal radiation, you have the Poisson distribution, and the statistical properties are very different from each other. In fact, a way of testing to what extent radiation is coherent is actually take a cavity and make a small hole in it and then count the statistics of the photons that come out, and depending on what distribution you get, you can deduce the amount of admixture of thermal and ideal radiation. And this is the part of photon statistics, the theory of photon statistics, which I do not want to get into, but I thought I would show you how fairly straightforward and simple ideas starting with a harmonic oscillator actually help us to get into quantum optics. Okay. So I do not want to say any more about this except to now look at a model of atoms interacting with radiation. We talked about in the blackbody cavity atoms are absorbed and emitted, etc. We would like to know, is there a simple model of interaction between atoms on the one hand and radiation on the other. That will take us to perturbation theory, and that is the last topic I want to do. So the next time I will talk about that.